questions from that? From the quiz?
Corrections?
Yes, you can do corrections to any quiz, any test, except the final.
How many points do you get if you do corrections?
So if you got an 80 or above, you can get 5 points back max. If you got like an 83, you can get up to an 88. If you got a 98, you can get up to 100. So 100 max.
What do you get lower?
If you get below an 80, you get a point for every 4 you missed. So if you made like a 64, how many points did you miss? 36 divided by 4 is 9, so then you can get that many points back. Maximum. Do all the corrections, get them all right.
What do they do?
What do they do?
Test.
Day of the next test. Like that. It sounded like a guess, but you were. But yeah, always test corrections, quiz corrections due by the day of the next test. Yeah. Yes, I have it for you.
Yes.
Evil. We suddenly did not do them anymore. Do it once. Any other questions from the quiz? Yeah.
I have a question on 2B.
2B?
2B.
So everybody's 2B, you could actually just factor that. I appreciate the synthetic, it's fine too. If you gotta factor it or you don't think about it, synthetic division works fine too. Bless you. Was there a specific question about it?
Well, I just said 2B.
Oh, I just felt like saying 2D. 2D, you have to come in and show me, for example, if you know the x-intercepts are -5, -2, and 1, and you plot those, that's nice. But then you have to, and then you know the end behavior, and you know if it touches and all that kind of stuff is great. But you need to figure out how, like if here it touches, let's say, you have to know how deep this goes. You need to plug in something. So that's what I meant by you might need to plug in some other points. So here you might want to figure out what f of -3 is, just to get a feel for how deep this goes. So I don't know how deep that goes, and then it goes up. I don't know how tall this goes, so I have to figure out, what's f of -1, or even just the y-intercept there helps out. When I ask you to find the intercepts, be careful. I mean the intercepts, the x-intercepts and the y-intercepts. So I don't know, do you have a more specific question about it? So that's where you put everything together. And very often, obviously, that's going to be the hardest part. Right? So here, can somebody tell me, from what I've drawn so far, let's say this is my sketch. And this is kind of an interesting question, too. Can you tell me what the equation of this might be? What's got to be true about -5, where that came from?
0.
Okay, cool. So it's got to have what factor in it?
Or even.
All right, good. I like that too. It's got to be some even power. Let's hope that it's just squared. Let's say that. X plus 5. How are we doing so far? Is it cool? So notice that I have a root of x plus 5 because there's a 0 of -5. I know it's going to have some even multiplicity. Since we're just making something up here, what this might be, let's go ahead with a square, but it could be a 4th power. It's just something that makes it touch or turn, right? Not go through. And at -2, what root does that have to have? X plus 2. And it has to be some kind of what power? Odd power. Let's say a 1st power. What the hell? And then at 1, what root's going to have? X minus 1. And let's say it's the 1st power. Again, it's got to be some odd power and then let it go through. Cool. So I've kind of done it backwards here. Normally you start here and you go, okay, it's going to touch at -5 because it's an even power. Or if you want to, you can do this. You do it, Jack. There you go. 0, 0. I saw a few people doing this. Which is perfectly fine. You can do your plus minuses. That's fine. Yeah.
The one in the middle should be x minus 2.
What's a negative 2, 0?
Okay.
Yeah.
How about you pointing on the top?
Now there's one last thing actually that we should include here. What kind of end behavior is this? So what should I really put out here at least? Negative sign. So now it's a downward parabolic kind of thing at the ends. Because it's got an even power overall, doesn't it? It's squared, cubed, fourth power overall. How many turning points does it have? 1, 2, 3. That makes sense with the fourth power. Cool. I kind of like that problem. Backwards. Sometimes I do that. Give you a backwards problem. Yeah, given this, give me one example of what it could be. You can build it up from what you see here. It touches here, you know what the zeros are, so you know what the roots are. You know what it does at each root, so you know what the multiplicities have to be. That kind of thing. I don't know if I answered your question backwards there or not. But you have to put together your knowledge of what the zeros are, what the multiplicities are, what the end behavior is. Right, so here I know the end behavior would be down because it's negative fourth power overall. I have to put all that together here. Right? And the nice thing is you can give yourself some more points. Like I was just saying, figure out what f of negative 3 is, so forth. Just to kind of anchor yourself a little bit more. Okay, so a few people didn't do any extra points, so you weren't sure how deep or how high things went. Especially if I ask for them, you want to do them. But in general, to do a sketch, you should kind of figure out just a couple extra points to see how high it is, how low it goes. Cool. Yeah.
Find the y-intercept, you have to make y equal 0, right?
To find the y-intercept, you make x 0. So in this case, it would be 25, 50, and then the negatives there cancel out. You guys follow what I'm doing? The number from here would be 25 times 2 is 50. The negative, so it would be my y-intercept would be 50. So I have to make my scale appropriate. Another problem a lot of you guys had was figuring out a good scale. If you catch yourself adding on to what I've given you, pick a better scale. Right? You shouldn't have to do that. So don't go, Jeff, man, what the hell? No, pick a better scale. Make it fit on what I've given you. Right? And I don't even pick my scale until I do a couple of these. And you saw that the other day when we were doing some of these together. If f of negative 3 is 187, I know my scale better be pretty damn big so I can get there. I don't care what my y-intercept is. If it's 1, shit, that thing's going to be damn close to 0. Oh well. I just want to be able to see what I need to see from what I've been given. Right? Yeah.
How do you find the intercepts on 2b?
Oh, let me see. So the nice thing. So if I give you a function like this, why is that a nice function to start with? One of the first things I want to do is find the intercepts. The x-intercepts jump right out at me. The y-intercepts will take a little work, or the y-intercept. It's a function. If I give it to you like this, so here I can see the x-intercepts are easy. If I give it to you like this, what's easy there? Y-intercept. I can see it's fine. Right? So if it's like this, the y-intercept I can see. To find the x-intercept, I have to try to factor this, right? If it's possible. If it's like this, I can see the x-intercepts. To find the y-intercept, I have to do just a little bit of work. Obviously, this is really nice because factoring is normally the ugly step. You know, give it to me factored already. I'll deal with the y-intercept. Okay, is that cool?
Yeah.
So in that one, you have to factor that bad boy. And you can either do this in synthetic or grouping. I made it so the grouping works. Yep. Say again, sir. Oh, finding the, oh yeah. Actually, I'll do this. there's something in the homework I've noticed, a little bit of homework that I've gotten. So find f inverse, yeah, that was his thing. Find f inverse for f of x equal to, one of my former students had a really good idea about making the root symbol officially that. So you can tell where the hell it ends, and I thought, damn, that's a good idea. A lot of times people just suck that 7 and make it 2x plus 4 inside, and that's a totally different problem now. So I might start doing that. So, how do I proceed?
Subtract y minus 7.
Yeah, so we got y equals 4th root.
2x minus 3 plus 7.
Okay.
Or plus 27.
So now you can, if you want to, now the book I think does it a little bit differently. I switch them right now. So it's a habit I have to develop still. And then I just solve it for y again, right? Not a big deal. Don't make a big deal out of it. Here's what I do first.
Subtract 7.
Subtract 7.
Yeah, subtract 7. And then I can do what?
Take it to the 4th power.
4th power. Right? 4th power. Then add to 3, right? And then divide by 2. And there you go. So then you can officially call that f inverse. If, now here's where things get kind of interesting. This is only invertible. And there's some problems in the homework that are like this. They're not as ugly as the one I've given you here. If I have even powers like this, what's wrong with them wanting to be inverse functions? What must be true for a function for it to even have an inverse in the first place? Has to be invertible. I like it. No, sorry. Yeah, in anything to a 4th power, it's been moved around and shit. It's been moved over by 7, and it's 1/2, and there's a 3/2 up, and all this kind of crap. So it's been moved over by 7, and it's up 3/2, so it's going to be roughly like that. Right? That's obviously not going to pass the horizontal line test. So what must be true then? It's not that difficult, really. You just want to cut it in half right where? So that it will pass the horizontal line test.
7.
Yeah, right at 7. If you just cut it there. You guys see that? And you have to be a little bit more careful than that. So if I said x greater than or equal to 7, that seems to work. But you also have to make sure that that choice, well, it gets a little bit freaky. That it makes sense for what you had in the beginning. To consider the range of this guy. The ones in the homework problem are a little bit easier. You just have to be careful anytime you have a function that's squared. And you're trying to find the inverse, you have to restrict the domain. You cannot use the whole x minus 2 squared here, can you? You have to, very first thing, you have to kill half the domain so that it'll actually pass the horizontal line test. This is a really good thing to keep in mind when we hit trigonometric functions. Oh yes, it's difficult to say by itself. Functions from trigonometry. Right? When we hit those, anybody know what a sine wave looks like? I mean, if you've seen the horror movies in the back are those oscilloscopes, right? Would that pass the horizontal line test? Now, that thing is like the worst thing in the world. It freaking goes through 1,000,000 times, even more. So we have to really restrict the domain to just be one little thing. Don't let it come back on itself. Don't let it come back down on itself. I have to really restrict the domain, and people easily forget that when we're dealing with inverse trig functions. We haven't even talked about trig yet, but it's just this idea. I cannot use that part, because that won't let it be invertible. Okay. Does that answer the question over there? So you have a 5th power, right, or a 5th root. Cube root? Okay. So you do basically the same thing. So really at the heart of this is just algebra. Can you resolve for that variable? the end. Yeah.
My question is, for this example, f of x, we know the inverse of f of x, right? Then we omitted out of it. But here the example is for g of x, the original function. So we should work on the original, right?
Well, the original function here, yeah.
Yeah, so we should work on
Well, this is dealing with the inputs for this original function are
This is-
restricted,
this is
which
not-
means the outputs for this are going to be restricted in the same way.
So which one we should take the interval for the inverse for the original? This is
What's the smallest output this can have? Let me try it this way. Guys, everybody. What's the smallest output that this can have?
7? 0 is when the
Negative.
2/3.
What's the smallest the fourth root can be? Can a fourth root be negative?
0.
No.
Yeah, the smallest it can be is 0. I heard you. I just want everybody to be on the same page. So you're right.
So the
The
output-
smallest output this could have is
7.
7. And then once I start plugging anything in for x, it's just going to get bigger,
Yeah.
right? So the outputs for the original function are from 7 to infinity.
This is output.
The inputs for the inverse function have to be the same. Let me say that again.
Yeah, yeah.
Alright, because I really want you guys to understand. What's the basic idea behind f and f inverse? How do you, if I give you a graph, how do you graph the inverse? What do you basically do? You take a point and you switch them, right? So aren't you really saying the range of one becomes the domain of the other one? Poop, right? Very strange sound effect to decide. There's math poop. Alright. So this guy's outputs will have to be this guy's inputs. Because what is the inverse function supposed to do? Take the outputs of this back to what the inputs were.
So this limitation is for the inverse, x greater than 7, while there
Yeah.
is for the input. If we
I want you to be really careful. These, now there's where I really don't want to get
So
too
we want-
detailed, because we're going to get confusing. This x is not the same as that x.
Yeah, I know.
Cool, alright, good.
So we are working on the output. What this is my question. If we find the inverse, that there is limitation, we work on the input or output? Which one?
Alright, here's the best answer to your question. If I were to graph this fourth root function, can somebody give me an idea what it would look like? Yeah.
I7 and
Don't stop trying, but no. Right, the fourth root's gonna look like this, and it's been moved around, right?
Yeah.
Not a big deal. Will that pass the horizontal line test?
yeah.
Yes. I have no concerns with him. It's just when I invert it, now in fact, think about it this way. Remember, how do I invert this visually? What line does it have to kind of flip around? Y equals X? So when you just do flip like that, isn't that the upper part of a parabola? Isn't that what this is trying to say?
Yeah.
All right, cool.
So
Coming
there's no
together.
problem.
Come.
There's no problem.
There's no problem.
Yeah.
This guy has no problem at the beginning because a root automatically means the positive side. It's the principal root. You guys with me? That's why it's only got this piece, not this piece. But when I find the inverse, that's a fourth power. Doesn't it have both sides? Inherently? Shit, I better cut one of them off so that it's still truly invertible.
So when you were saying about the other one, how you have to cut off half, how do you know which half to cut off of that one?
Well, you can do several things, and one of the easiest ways for me to do it personally is the smallest, this could be a 7, and it goes up. So then I know this has got to be 7 and up.
For the other one that you're talking about, like if we wanted to find the inverse of that.
Oh, and if you start with this, you could actually define it to be one or the other side, to tell you honestly. So they have to, if they give you this, they have to, you'll notice this in your homework. They'll say this,
Yeah, I
so then that would be the upper part, you know,
Yeah,
the
okay, understood.
right side.
Now it's clear. Thank you.
Good, okay. All right. Got a few people with me. The rest of you want to kill? Yeah.
I have a question, like, like the inverse, what, like, there's application for it in real life, like, they use it for what? I tried to Google, but couldn't find a good answer.
All right. Here's the good answer. All right, now, okay. So I'm operating on the assumption that we all understand that math itself is incredibly useful. If you don't believe that statement, it's a bad place to be starting. Right? If you don't believe math is useful, I don't know where you're getting your motivation to get through this. Right? And number two, you are wrong. I want you to desperately understand it. Not just because I want to defend my position as a math teacher, but because it's just freaking true. There's so much stuff that we've done that could possibly do without mathematics. And all of it has to comes down to at some point solving some kind of an equation. So I have an equation that deals with my power input. And I can't let it be greater than something. So then I solve that to figure out what my whole setup has to be, that kind of thing. So you're with me on that?
Yeah.
So, I mean, how do I solve that equation?
Square.
And how do I know to do that? Because I know that the square is the inverse of the square root.
Just next would be 9.
Yeah. Right? And so, I mean, that's the most fundamental thing. We've been doing inverse functions ever since you first learned how to solve an equation. You've been doing inverse functions. They're just incredibly simple inverse functions, right? Multiplication, division, yeah. There is no division, it's just multiplication by the inverse. I mean, there's stuff like that. Yeah. So division is just the inverse of multiplication, so that's why there really is no division. It's just flipping things over.
Is there a button you can hit on your calculator to graph the inverse?
Yeah. There's several. Graph 1 divided by x. So I don't know. How do you mean graph 1 over x?
Like if you put in an equation.
Oh, I see what you mean.
And
Not
then
that
you
I know
just
of.
wanted to see what. Okay.
Yeah, I don't think it can do that yet. Okay. That's awesome. I love that kind of thing. So before we get back into the stuff, any other questions? Specific or general? Oh, and real quick, before I forget, we've got a couple of homework to do. Talia, Sam. Yep.
Question 36, number, page 244.
36.
Page, yeah. Section 3.
All right, guys. Two things you would probably worry about when you first see this is the 1/8 out front and the square up there, right? But a simpler problem, if you had to factor this, all you do is you factor what's in here, and how many of them will you have?
2 plus 1.
You'll have 2 of each, right? If you factor this, what do you get?
X plus
X minus
9, X minus 3.
I know what you meant. And then you just have 2 of each. So now the multiplicity will be 2 for each one. Oh, no, you with me? So that square is not going to bother me. I'm really going to focus on the inside, and whatever I get, I'm just going to square each piece. Each piece is going to have a multiplicity of 2 now, because of that big old square sitting out there. The 1/8, screw him till the end. Okay, don't worry about him. He's already been pulled out for me, thank God. So how do I start trying to factor this? Bless you.
Execute. Take out.
No.
Square it.
What?
Factor by grouping.
Plus a 3.
Oh, you mean, okay, gotcha.
Yeah.
I thought you were trying to stick it out everything, but you mean, good. Whenever you got 4 terms, first thing you try before you do anything is will grouping work? And it looks like 2 to 3 ratio is true in both. You guys see that?
Yeah.
This is 8 times the ratio of 2 to 3, so it looks like it might work. So if I take out an x cubed, what do I get?
Okay, 2x plus 3.
And I take out a,
8.
what kind? Negative?
Negative. 2x plus 3. X cubed minus 8.
Factor out.
Yeah, this
the
was
minus
nice.
3.
Looks like one I would make. So then you get the 1/8 comes for the ride. X cubed minus 8 squared. 2x plus 3 squared. Only squared because of that. There's only one of them that I pull out, but then it's squared because of this dude. Right? I don't want people suddenly thinking grouping works different. So far, so good. All right, it looks a hell of a lot better than that did. And that piece, of course, you can go further with.
Difference of cubes.
Difference of cubes. Yeah. Little dude, big dude. They're each going to be squared. I know this is one of your favorites. Good. This is
X minus
3 x's, 3 2's, so 1x minus 1 2. The other
X squared.
2 x's and the other 2 2's. Opposite sign,
2x.
product in the middle. Don't like that exclamation. Okay.
The problem with second.
Let me slow down. Let me go back. Any cubes will basically be the same idea. So if I had x cubed plus 27, for example. If you need to, you can also do what I do when I first teach this. Write for yourself what the pieces are. Right? Cut them into 3 parts. Just like you cut a squares into 2 parts. And you put them in. 1x there plus 1 3 there. So the other 2 x's have to go there. So then they get x cubed. The other 2 3's have to go there. So then they get 27. There's always only one negative in the whole thing. It's either here or there. Since it ain't there, it must be there. What's the middle dude? Product of the stuff in the little dude. Always. Cubes are always the same. Yes, sir?
I have a question. Like the second step is equal to 0, right? The whole equation.
The entire thing.
What do you mean the second step?
Zero.
Like equal to
Yeah, I'm just factoring it.
we don't equal to, like we cannot equal to 0 on some so.
Oh yeah, sure. Because it asks me to find the what was this?
0.
36. It just said, oh, factor it all the way and then use the factored form to find the zero.
Yes, find the 0.
Yeah.
Because I thought if we equal to 0, we can just cancel that.
Can I factor? Can I really factor anything else? Truly? Technically, I could factor this now. Do we understand that?
Oh,
Yeah.
If I use quadratic formula on this, I could rewrite it as x minus one piece, x minus the other piece. Do you remember that? It looks disgusting as hell. We don't really do that very often in practice. So I'm thoroughly fine, unless I specifically say, use quadratic to factor this,
Yep.
which I might. You can just find the zeros now, right? What would the zeros be?
Plus x. Plus 2.
Only
Equal to
2. Negative 2 won't make any of these that I know of 0, right? Only 2 makes this 0. What makes him 0? Maybe 3 halves, right? Subtract the 3, divide by 2. Okay. And then I gotta figure out this guy, and I do him by quadratic. Yeah. Negative b plus or minus the square root of b course. Blah, blah, blah. So it's gonna come out to be
-1 plus minus I.
good, complex. Cool. I know it's complex because it's got a negative end of the square root. So you have two kind of ideas there, and they kind of go hand in hand. And if you kind of mix them up a little bit, I'll give you some leeway. You've got the factoring, and you've got the finding zeros. If I just say factor this all the way using irrational and complex. That means factor this all the way.
So what would you want us to leave?
So here we go. What do you get here? -2 plus or minus. You get I. What's radical 12? 4 times 3, so a 2 comes out. And everything can be divided by 2. So how would I officially factor this? X squared plus 2x plus 4. How could I factor it then? X minus. Yeah. X minus -1 plus radical 3, x minus -1 minus radical 3. I. Do you guys see that? That number is disgustingly ugly, and so we lose the connection that we had so easily before. If I solve x squared minus 9 equals 0, if I solve that, what do I get? Don't I get plus or minus 3? So then how do I factor this? X minus positive 3, x minus negative 3. Ooh. But when they look like that, holy shit, I forget that it's just that easy. I don't care what the factors, I don't care what the zeros are. X minus one of them, x minus the other one. X minus disgusting, x minus, who cares? You're almost done. You just have to bring the negative in. Bump the I. Okay. So what would happen if I multiply these together? That would be kind of disgusting, wouldn't it? But what would actually happen? About that, of course. Right? That's what we just proved. That sounds like a question I might even give you.
But then,
Multiply this out. Right?
so what do you put as the answer for the 0?
Well, the 0 is
Minus that.
this. Right? That would be the answer if they asked for just the zeros. If they asked for it factored over complex, irrational stuff, that would be the answer. This one.
So if they ask for 0, then we get a complex answer. Still put it?
Say again?
That's complex.
Yeah, oh yeah, sure.
You will still put it?
Oh yeah. Remember, after section 3.5, complex numbers come in.
Okay.
Complex numbers round us out. Because now if you have an 8th power, you must have 8 answers. Some of them might be complex. Without complex numbers, they don't match. It doesn't make as much sense. 8th power can have 1 answer. Shit. It's not good. Okay. Break 1A. All right.
Okay, sorry, Chef.
Yeah.
I want to put it in the draw. When I draw, how can I?
When you draw,
When I draw, yeah.
I don't think they ask you to draw.
No, I know. But if I want to put this point, -1
Oh.
plus minus, yeah.
Are you asking me how to graph this?
Yeah, how graph it?
You can't.
Okay.
Because what's the only graphs that we're dealing with? The graphs over the real numbers.
Oh, yeah.
There are graphs over complex numbers, but they're different. There's 2 main ways to graph complex numbers. You can either, now this sounds interesting.
Yeah.
This is nothing that's going to be on the test, so I might lose some of you right there. So we got to turn around somewhere else. One way to graph complex, real quick, this is going to take less than a minute, is to graph the real part versus the complex part. So it would be 4, -3. That's the less interesting way to graph complex numbers you can imagine. The more interesting way is like stupid more interesting. It's a lot more complicated. And that's the one I'm telling you about. You graph a function, and it actually, the color that's in that region deals with how complex the answers are in that region. So that's the more interesting. That's where you get things called fractals. That's one place fractals come from, is graphs of complex valued functions. Wow. Look it up. All right, that's enough for that. Is there anything else from the quiz or anything? Homework? Okay. many guys have done logarithms before? Anybody? How many guys, is that the first time where like you've only heard that word in passing? Anybody not really done them much before? Okay, okay. We're not doing logarithms, I just want to ask. No, we are doing logarithms. That was funny. So the first couple sections of chapter 4 are just exponential functions. And then we get into logarithms, and it has to do with the question from earlier. If I have exponential functions in an equation, how could I solve them if I don't know that exponential function's inverse? Like if I didn't know subtraction existed, I could never solve x plus 2 equals 8. Because I have to subtract to solve it, right? Yeah.
These are all gonna be on the test or exam, right?
Oh yeah.
The exam will be from,
What day is the exam?
Monday.
Monday, good. You didn't realize that? It's no longer Wednesday. Wednesday's review. The test is on Monday, week from today.
so when we reach or
Exactly. However far we make it today,
okay.
which I will control. So to me, the unfortunate thing with mathematics is it's so easy to lose sight of the creativity and the flexibility there is in mathematics. One way I always teach exponential functions is just to start off with saying, where have we not put the variable yet? You know, when I'm teaching my 110 students, where has the variable not shown up yet? Which sounds like a very strange question. They're not really sure. They're looking like, what do you want me to say? It's one of those questions. But up to this point, we've seen stuff like x cubed, we've seen stuff like square root of x, we've seen x under roots, we've seen x on top and on the bottom of stuff, and we've seen all the crap this leads to and all that kind of stuff. You with me? So we haven't seen it as itself a power. So one level of mathematics is just realizing you can play with this stuff. What would happen if I did this? Try it out and do it. What would happen if I did this? Try it out and see what would happen. You're getting to the point, and this is the first class, where you have to feel comfortable to play. Trust me. And you don't know what I mean yet necessarily. But chapter 5 and 6, if you don't feel comfortable to play and they go, that didn't work, that's fine, let me try something else. I mean, that's going to happen to you a lot. So that's what real math is just going, okay, well, let me try to do this. That didn't work, let me try something else. That's what it is. So we haven't seen a function like this yet. We haven't worked with it in this class anyway. Hopefully most of you have seen this at some point, but we're going to review it. So normally the first time we hit a function, what do we do with it? We try to visualize it is a good thing to do first. We try to graph this thing. And in the process, we play around with how does it deal with numbers? What kind of inputs can it take? What kind of outputs come out? So make a little table. Of course, we're not going to do too much of that in here. So what kind of inputs? Is there any restriction on the inputs? Is there anything that I can't raise 3 to? I can raise 3 to a negative power, right? What's a negative power mean?
1 over.
Flip. How about a 0 power? I just move 1. So no matter what base I put there, when I put a 0 in, it's going to be 1. That's interesting. So I could put in there negative 3, negative 2, negative 1, 0, 1, 2, 3. I could put fractional powers in there too. But I'm going to do these first and see if I really need to investigate that. What do fractional powers mean? Anyway. So what would 4 to the 1/2 power, what would it mean?
Square root.
Square root of 4, yeah, which is 2. So fractional powers are roots. The bottom is the root, like on plants. The top is the power. So if I had 4 to the 3/2, that would be the square root of 4 to the 3rd power. So it would be 8, right? So good little review too. Okay. So if I wanted to, but that's an ugly base for that. If it was a 9 base, I could do a 1/2 in here. That would be nice. Putting a 1/2 in there, getting square root of 3 is not really something I want to try to graph. So forget it. So what do you get when you put a -3 in there?
Negative. Negative 27. Negative 1/27.
Yes, cool. So a power can never make the thing negative. Never. You can't raise a positive number to a power and make it negative. There's no way to do it. Because the exponent basically tells you how many of these you've got. So is there any way I can have any negatives in there? 3 to the 5th power would mean 5 positive 3s. 3 to the -4th power would be 1/4 positive 3s. So is there any power that I can suddenly make this become negative? No, don't forget that. We're actually going to see that in the graph. It's going to be nice. So 3 to the -3rd is just 1/3 cubed. 127. All right, so let's try this one. -2.
1/9.
1/9. I love it. So 3 squared is 9. 3 -2, 1/9. Just like that. -1.
1/3.
1/3. 0.
1.
1. 1.
3.
3.
9. and
Squared is
27.
9. Cubed is 27. There you go. You see some nice symmetry there, right? Sort of. Kind of weird symmetry. 1/over that symmetry. So let's try to graph this thing. Let's see. So let me make my scale. My fractions will be ugly to do this, but I want 2, 4, 6, 8, 10. That's 1. So -3 is 1/27. So obviously on a graph you're not going to be perfect with this. I'm just going to make it very tiny. -2 is 1/9. Just a little less tiny. -1 is 1/3. Ever so slightly less tiny. Okay, so far so good. And then 0 is 1. 1 is 3. 2 is 9. And of course, I'm okay with leaving off 3 is 27. That just kind of, you can't graph it, but it gives you an idea that it goes up pretty quickly. So if I try to put these together, this is pretty easy, that side. It's going to keep going up forever. And that's disgusting. Too bad. What's happening on this side? In fact, it goes with what I just said. It's going to keep getting closer and closer to 0, never get there, so of course it is an asymptote. I love it. It's asymptotic at 0 back there as x goes to -infinity. So this is a good example of a function that's got an asymptote only on one side, really. Right? Okay. So that just keeps getting closer because 3 to the -billionth is 1/3 to the billionth. It's tiny as hell, but it's still not 0 because the top is 1. So there's no way it can equal 0. It's damn tiny, it can equal to 0. Okay. Cool. Now, of course, one piece of this, I just want you to be ready for this. One thing I could do with that is what we've done before. What would happen with this should not bother us. But you're going to see this every time we hit a new function. We're going to talk about this type of thing. And what would that do to that graph? Shift it.
By 1.
Careful. What letter is the 1 with? It's with the x, so it's going to move left or right.
Right.
It's going to move good. The opposite of that, it's going to move to the right 1. So every single point is going to move right 1, right 1, right 1. I think we get the idea. So now it's like this. You guys with me? So I promise you, any function you can come up with, if you put a x minus 1 and place it x, it will just shift it. Whatever the hell it looks like, it's going to move it over. There's another sound effect. Let's see if we can get it. All right, and you know, I could just keep going all day, but if I had g of x equals 3 to the x plus 2 minus 5 What would the shifts there be? Good, left 2, down 5. Alright, put a negative in front. What would that do? Yeah, all the outputs used to be there, now they're going to be the negative of what they used to be, so it's going to go like that. Good. I like it. Yes, sir.
Will we ever get like an inverse of that?
That's where we're going next. Or, eventually, very soon. Like I said, if I have this sitting in an equation somewhere, can I solve it? Currently, in this class, with what we've talked about, no. Because what's the opposite of this? I don't know yet. You with me? So if I have x divided by 7 equals 2, I can't solve it if I don't know multiplication, because that's the opposite of division. So if I have this in an equation somewhere, like, for example, 3 to the x equals 11, you can approximate it. Can somebody tell me what x must be around?
A little over 2.
3 is too much. It's in between 2 and 3, closer to 2, because 3 squared is 9, and that's not that far above 9. You with me? So just to make something, this is what I do. I'll say like 2.07, and then it comes out close to that. And I'm like, what? Right? It's got to be a little bit above 2. But I can't really, can you solve it and get exactly what x is? Not right now. Not with what we know in this class. I'm going to be careful. Some of you guys know how to solve that, maybe. Yeah. So there's really not too much in this first section. Nothing overly interesting. Yeah. Nothing really. So, real quick, just to look at the homework so you can tell what's coming. They ask you to use a calculator if you know how to use a calculator for a to the button. Right, everybody know where your to the button is? You know what I mean when I say that? 4 to the 7th power. You know how to do the to the. If you have a graphing calculator, it's your little caret. If you have a scientific calculator, it's like an x to the y button. Okay, so there's a little section that says use a calculator. The student should go, yay, they said I could use the freaking calculator. Should be good times. Sketch a graph by making a table of values like we just did right now. Blah, 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 blah. Graph the function by starting from graphs in figure 2 and translating it, transforming it, shifting it around. Okay. And then, of course, it gets a little more interesting at the end. Which one of these do you think would grow faster eventually? I mean, x to the 100th power grows pretty damn fast. You with me? But this guy's going to overtake him and just kill him eventually. In the small runnings, no. 2 squared is 4. You want to plug a 2 in and get 4. And plug a 2 to the 100th power, holy crap. But an exponential function will always eventually kill anything just about how its rate of increase goes. Okay, maybe you're with me. So x to the 100th power will win at first, but eventually that sucker is going to pass him by. Okay. What about this here? Let's see. Can anybody tell me what f of x is here?
1.
So it changes, so it has to be some function of x. What must that function be? Okay. So at 0, what is it? 1, right? So it hasn't been translated all up or down, right? Because when I raise anything to the 0 power, it's 1. So I know it's something to the x power. And what's 1? 1 has an output of 4. So what do I raise to the first power to get 4? 4. So it must be 4 to the x. And this is obviously me trying to be, what would that be there then? 1/4, 11. Right, 4 to the negative 1, 1 4. Cool. So you'll see a couple problems in the homework like that. They'll give you a finished graph and say, can you figure out what the function must have been? Okay. So section 4.1, very nuts and bolts, very basic. Yeah.
Would that mean that all those graphs would start on 1, no matter what?
Yeah, unless they've been shifted up or down, or left and right. Yeah, so that's why I know it hasn't been shifted, more than likely hasn't been shifted up or down, left or right. And before I get too far, what would happen that's interesting about this?
It would move up.
Everything would have to move up 1, which means the asymptote would move up 1. So you'd have to, if you wanted to draw that, you'd draw the asymptote here. And then every point goes up 1, up 1, up 1. So now it's like this. So that asymptote has got to move. So if you have a vertical shift, it goes up or down, you got to draw a dotted line somewhere. Because now the asymptote's not going to be on the axis anymore. It's going to move up or down. Cool. Semi-decent. It's no longer poker faces, it's anger. Go back to the poker. It's better. I didn't know how much you wanted to do. So, I mean, but really, honestly, 4.1, if you haven't seen logarithms, I'm hoping to God you've worked with exponential functions. If you haven't, find your teacher from last semester and say, what the hell? You really should have worked with these. If you haven't, though, they're not that difficult to pick up. You're going to be able to make some table of values. You can play around with it. Okay. And all section 4.2. I'll talk about 4.2, then we'll take a break. Break number 1 of 1. All section 4.2 does, it does something very interesting. If any of you guys have taken biology or studied this before, you should know this base. There's a very special letter. It's sort of like pi. Some of you guys know this letter. So where it comes from, here's to me what the most interesting place where it comes from. This is the function 1 over x. Stay with me now, this is kind of cool. Because there's kind of a lame place that this comes from, and to me this is a little bit less lame. If I start at 1 and move a little bit over, like if I stopped here, I could say what area this is here. You with me? So this, of course, 1 would have to go to 1, so my scales are different, so just deal with it. This area here, is it more or less than 1? I mean, that's a weird-ass shape, but you can tell me if it's more or less than 1. It's, careful, how wide is it? How wide is it? It's less than 1 wide. And how tall is it? Well, part of it's 1 wide tall, but the rest of it's not 1. So overall, it's going to have an area less than 1. You with me? So the interesting thing to me is if you go out far enough and you stop right where the area, that's too soon, Jeff. Right where the area is 1. Right where the area is exactly 1, that is the number E. Now I've written it up there. Have you guys seen the e to the x before you all that kind of stuff? And you use it very often. I like the example of throwing a couple rabbits in a room, giving them some food and wait. It describes the e to the some kind of power, describes the population growth in that room, right? Exponential decay, if you put some plutonium somewhere and you wait, e to the negative whatever, is going to tell you how quickly it becomes less and less radioactive. You with me? Semi with me? So that's what the uses of this thing are. So it's in between 2 and 3. Okay. And the other place this comes from, that's what the book talks about. This is interesting too, I guess. As n goes to infinity for this, f of n goes to e. That's a little less interesting to me. I don't know. So E is like 2.71828 blah, 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 blah. So if you tried this, everybody try this. Take your calculator out. You don't pretend like you're trying it if you really don't want to, but try it. Take your calculator out. Somebody give me a decently large value for n. 100. That's right. Let's try it. 100. So 100 plus 1 over 100 to the 100th power. So if you have a graphic calculator, you would do it like this: parenthesis 100 plus 1 divided by 100 to the 100th power. Let me do it with you. Overflow.
I got an error.
Oh, what am I doing? I'm sorry. Wait. Where did I copy that from? There's a 1 there. Oh, Jeff, you suck.
You can do it.
So then if you do this, what do you get? Don't graph it.
2.704.
Yeah, 2.70, blah, so it gets close to that. And the larger the number is you put in there, the closer that'll get to the value of e. And really think about what's going on here. As n gets really big, what does 1 over n do? Gets really, really small. It goes to 0. So this kind of goes to 0, and this goes to infinity, doesn't it? And what's 1 to any power? 1. I really want you guys to think about what this is saying. So this is saying this inside basically goes to 1. This outside basically goes to infinity. But it doesn't ever equal 1 truly, because does the inside actually make it to 1? No. So this is kind of neat. That number there is kind of like a little compromise. It says, okay, the inside wants to be to 1, and 1 to any power would be 1, but the inside never gets to 1. But it's close enough that the whole thing shouldn't go to infinity, so that kind of compromises it. We'll give it 2.71 and blah, blah. To me, I like that. It's kind of cool to step back and say, what is this really saying here? Why is it so that's not as lame as it looks on first blush. I personally just like that better, it's more visual. But this is still kind of cool too. Okay. Except for those of you who are falling asleep. All right.
Break.
Yeah. Let's take a break. Come back. 5 till.